Is that your laptop? That.
Yeah. Okay, cool. So Marco worked on a lot of things, including like interpretability, model evaluation. And if you work on similar spaces, it's really hard to miss his papers like Lime or Checklist and a lot of others. We got to know each other during our PhD, and we also collaborated on a lot of projects. Afterwards, I practically treat him as my external advisor. I learned both research and also how to communicate your research to different audiences from Marco because he's a really good presenter. So today he is going to talk about some more recent work he does around also debugging and model fixing. I guess the highlight would be AdaTest. It's a framework for people to iteratively debug and also fix their model, specific problems of their models with the help of large language models. And he will also talk about some similar topics of how to patch model problems with natural language, how to debug vision models, and how to avoid some conflicts in debugging process. So without further ado, take it away.
Thanks, Dong-Chuan. When you're introducing someone, you should never say that they're a great speaker, because you just set them up to fail.
That is the goal.
Thank you. So I apologize in advance. My slides are really ugly. I didn't have time to make pretty slides, so I'm already failing as a presenter. But yeah, I'll talk about adaptive testing and debugging. I have a tentative plan here to present 3 papers, 1 in progress, 2 that are kind of done. But if we only get to the first one, it's fine. So I'll make space for questions along the way, but also feel free to interrupt me. If anything that I say doesn't make sense, or if you have a question, it's fine to just interrupt, raise your hand, and I'll stop. But I'll start with this paper from 2020 in ACL that we had called Adaptive Testing and Debugging of NLP Models. So this is work I did with Scott Lundberg at Microsoft.
So can I interrupt? People on Zoom are saying there's a pretty strong echo on Zoom, so people who have their Mac open, or just mute yourself if you're on Zoom. Go ahead.
Thanks. So yeah, adaptive testing and debugging of NLP models. So just to start, I think it's pretty non-controversial that another problem.
Sorry, people are seeing the presenter view.
They're seeing my presenter view. Okay.
You probably want to change the screen that you're sharing.
I don't know how to share the other screen. Technology is really hard for me. I don't know how this works. Screen 2, this one.
Yes.
They can see my presenter view though, it's fine. I don't have notes that say speak louder here or something. Is it fine now? Okay, and you had a different question or the same one? Same? Okay. So I think it's not very controversial to say that there are bugs in NLP models. And by bugs here, I just mean behaviors that are not what we expect from these models. So if you have a sentiment analysis model like Amazon's commercial sentiment analysis model, you do not want it to say that I don't think I've ever had a nicer time in my life. Like this should be positive, not negative. Or if you have another model and you say, I'm for refugee immigration, that should be neutral or positive, not negative. We had this example from Google Translate where you translate this Portuguese sentence that means, I don't recommend this dish. And it literally translated it as, I highly recommend this dish, which is a bug. Like it's a failure of how the model behaves. And not to pick on Google, because Bing's Translate also does a similar thing where you say the icing on this cake is delicious, and it translates it to the cherry on this cake is delicious. I don't know why you would do that. So these models have bugs, but finding these bugs is not trivial. It can be hard. There are many reasons for this. One reason is that the bugs may manifest in ways that are highly specific. So for this Amazon model that had this problem there, I don't think I've ever had a nicer time in my life. You put many similar examples. I don't think I've had a better time in my life. I've a nicer day than this one, and predicts positive on all of them. So you may be thinking, is this even a bug if it doesn't manifest in all of these? But it does manifest in other examples. It's just that the space, the cut that you need to make is a little different. So I don't think I've ever been so well off is predicted as negative. I don't think I've ever seen a nicer town negative. So there is a coherent group that this model fails on but it's hard to find what it is without trying a bunch of different things. In addition, even if you find such a bug, fixing them is even harder. And to give an example, let's say that I fix the I am for refugee immigration example there. So I say this is neutral. And the way I do this is maybe I collect a bunch of new data where it says that this is neutral. What often happens is you patch a problem, you fix something, and you break something else. So in this case, if you add a bunch of stuff about immigration as neutral, it starts predicting everything that's about immigration as neutral, even negative or positive statements. Like I'm against all deportations should probably be negative. So fixing in such a way that you don't break something else is really challenging. And anyone who has tried to fix any fairness problem whatsoever knows that this is the case, or any bug in general. So what's the landscape? How do people do this right now? I think there are two categories of methods. I'm calling them user-driven and automated, and that just means who's driving most of the work. So in the user-driven side, I have checklists, which is a framework that I did for unit testing models. There's error analysis that Cherry did. And there's just plain crowdsourcing, something like Dynabench, where you just ask users, hey, try to make this model fail. What's good about this is that the user knows what the right behavior is. If I show someone a bug, they're like, OK, this is a bug. They know what's right and wrong. They can decompose. If I tell someone, give me sentences about immigration, they can decompose that and say, here are sentences about immigration. If they see a set of failures, they can figure out, OK, this is probably because of immigration. This is probably because of names like this and so on. But it's very slow, costly, and it totally depends on the user. So if you have something like checklist, I had this experience multiple times at Microsoft, where I would come to a team and say, hey, you should use checklist. It's great for finding bugs. And the team would be like, it's not going to work for our case. And then I would have to come in and say, hey, give me your model. Give me access to your model. And then I would find a bunch of bugs and say, here, it does work. And then they would be convinced. But even after that step, when they were convinced, what often would happen is that they would put a junior engineer on checklisting. And then the junior engineer would say, hey, I couldn't find any bugs. So there's a lot of variance between users. If you have an experienced user, super easy to find bugs. If you had a user that's a little less creative or with less experience, then they couldn't find the bugs. So user-driven really depends on who the user is and how they're feeling that day and so on. Automated methods, on the other hand, they're automated. Like you can get adversarial examples. You can get GPT-3 to generate examples and so on. So that's good. Oh, sorry, I forgot to mention that. Even if you do the user-driven stuff, typically it's hard to fix the bugs. If you just find stuff with checklists, you can't fix the bugs. So for automated methods, typically what you can automate is very restricted. Like you can get a model to perturb the input without changing the semantics a lot. And you get a particular kind of bug where models are too sensitive, for example. But you cannot get an automated, it's not that you cannot, but it's very hard to get an automated method to explore what happens when you have sentences about immigration. What if you have sentences about immigration that mention stuff with the Trump administration? Like the automated method is just not going to try that. So it's fast and cheap. It's easy to do trial and error, but it's very restricted. So in this paper, AdaTest, what we're trying to do is to get the best of both worlds, combining the strengths of both approaches. So adaptive testing and debugging, or for short, AdaTest, is basically, it's very simple. We're going to have a human and a language model working together. And the way the loop is going to work is the language model is going to suggest tests. So the user here is trying to find bugs in a model, or they're trying to write tests. The language model is going to suggest some tests. So that it feels like the automated method that I just talked about. But then the user in this tight loop is going to filter some tests and organize what the language model is doing so that you do get the best of both worlds. The language model generates a bunch. It doesn't need to be precise. You only need recall. If it generates 20 tests and 2 of them are reasonable and find bugs, that's good, because the user can just look at those and say, these 2 are good. And if you can get the language model to improve in this loop, which is what we do, then you get the best of both worlds. So the language model is making the suggestions, doing the creative part. The user is doing the evaluation part and a little bit of organization. I'll make this a little more concrete, but we're calling this the testing loop. We're going to have 2 loops. This is the first one. And now I'll show you a little demo with a previous version of the interface. I'm sorry if it's kind of small, but I think what we're showing here is we're within a focus topic. So if you can't read, that's saying clear positives. So we're doing sentiment analysis here, and we're starting with a subset of examples that are very easy. I really like the food. This was the best food I've ever eaten. I really enjoyed it. And so this is our focus topic. You have some tests here that the user seeds the thing with. And the model succeeds on all of this. So the model is passing on all of these tests. So remember I told you, so this is passing. Pass is green, fail is red. And it's saying should be positive. So I told you the model is going to make suggestions of tests. The way it happens is the user clicks this button. And in the back end, we're getting GPT-3 to generate more examples like these ones, so more clear positives. And this is what it generates. And they're being ranked by their whether they fail or not. So how not positive are they? So the top one is actually a failure of the language model. They need to start serving teriyaki soon. I don't think should be positive. At least it's not a clear positive. So the user can just disregard that one. But the second one says, I really, really like the food. And the model is failing. It's not predicting positive on that for some reason. This is, by the way, a commercial model that Microsoft sells. So it's not some research model. Like people pay money to use this, and they paid money to train this. So this shouldn't happen. Anyway, you see that the language model generated quite a bit of examples, and the user can maybe select which ones they like. In this case, this dish is really special. You're never going to find a better place to eat. And what the user does is they add them to this topic. Like we're within a specific topic called clear positives. So once I add this, my topic now has more examples. And what that's going to do is the next time I click suggestions, GPT-3 will take these into account. So you're going to get a hill climbing behavior where GPT-3 is iteratively going towards what the user is selecting. So GPT-3 is kind of learning to produce more suggestions that produce failures and also that the user likes. So suggestions that the user is interested in. So if we click suggestions again, you have a lot of examples. And now you have a bunch of, like you have one specific behavior that appeared in one example down there. You're never going to find a better place to eat. Where you have this kind of negation followed by greatness. I haven't had better. I've never had a better meal. I've never had anything better. So it just picked up that pattern. We didn't start with this. We started with clear positives. But one little piece of feedback from the user got GPT-3 to generate more of this. And this is not cherry-picked. Like this was an actual session that I ran. And this happens all the time. So at this point, I said that the user would label things and maybe organize them. We have a coherent group here that maybe we want to organize into a new topic and explore more. And a coherent group that says, I've never had better, basically. So I created a topic that says never had better. And now if I hit suggestions here, my suggestions are going to be conditioned on these examples. So they're going to be even more targeted towards this. And sure enough, if I click suggestions, I get a million examples of this. And now I'm convinced that the model is failing on this, because I can produce 20, 30 examples where the model just cannot handle this pattern. Question?
Maybe I missed that. On the right side, this bar, what does the length indicate here?
Yeah, sorry, I didn't say that. But the length indicates it's like a failing score. So if I'm saying that it should be positive, a failure score of 1 is saying the model is assigning 0 probability to positive, basically.
And red means it's
red means fail, green means success. This is an old interface, so you don't have to tell me it's bad. I already know. But that is what it's doing. So this one here is failing just a little bit. It's almost predicting positive. And we do the prompt in such a way that the more something is failing, the more likely it is to end in the prompt and to be towards the end of the prompt. So GPT-3 is biased towards failure in this case. OK, so maybe let's go back to clear positives. Maybe I've exhausted this topic. So I'm going to, oh, sorry, this is a new topic. I skipped a few steps in between here. I created a new topic that says really good. So basically, it has the word really a lot. I really, really like the food. As you can see, I really like the food. So this is another topic that we found. And if you click suggestions, it's going to find even more. So it finds stuff like I really like the ribs. I really like the dish. I really, really like this. And this illustrates something I said in the beginning. Because if you look at these two examples highlighted, I really like the food is not predicted as positive. I really liked the food is predicted as positive. So if you're a human tester, trying to figure out, does my model predict well on sentences like I really like the food? If you happen to pick I really like the food, you think the model is working. You have to run into I really like the food. Of course, this is a failure of the model. The model should work on both of them, but it's just that this happens a lot, where there are some patterns that seem kind of random like that. Okay, so let's go back to clear positives. Now I have two topics. You can ignore those encodings there on the right because they're old news. But I have two topics, a bunch of failures on each. Maybe I click suggestions again, and now I'm going to get new suggestions, and maybe the user will see new patterns and will come up with new topics. And this is a loop. So they're iterating on this very quickly. With 5 minutes, you'll find a variety of bugs here. So I did have an example here because I want to pick on myself in the past. So I had this paper checklist, and I tested this exact model that Microsoft sells. And I have a sensitive category here for tweets that have stuff about sensitive stuff. And I'm saying this should not be negative. So I love to see women succeed should not be predicted as negative. It's a three-way model, so it can predict neutral or positive. So should not be negative is just saying should not be negative. Positive and neutral are fine. And for this model, when I was writing checklist, I wrote a few templates to try to find bugs in this model. And I was motivated. Like, I wanted to find bugs in general. I did find a bunch, but I wanted to find this kind of fairness bugs to put in my paper. And simple templates did not find bugs on this or Google's model and so on. So I said in the paper, hey, the model predicts this stuff as neutral. And I even hedged. I said, look, absence of failure does not imply that these models are working, just that I couldn't find them. So let's see if AdaTest finds bugs. I start with very easy examples. And this time, the first round of suggestions doesn't give me any failures. So everything is green there. But you see that it's slightly less green. So the bar is a little shorter. So maybe I'll add some of those examples, like being with African-American women has enriched my life, should not be negative. Hip-hop culture, I'm a feminist, none of those should be negative. I add them in, and then I get more suggestions. So now in the second round of suggestions, I already find one bug. I'm a God-fearing, Bible-believing Christian. Microsoft does not want to predict this as negative, like this is bad. So maybe I create a topic out of that, and now I find a bunch of examples about I believe in God, I believe Jesus rose from the dead, I'm a Bible-believing Christian, and all of these are predicted as negative. So it's nice that an expert tester could not find this kind of problem, but 2 rounds you find it. And also found a bunch of stuff about African-American women that the model really likes predicting as negative. So I refuse to stop dating African-American women. I've dated a lot of African-American women. I empathize with African-American women, predicted as negative, and so on. And you can repeat this with any sensitive topic of choice. And for this particular model, basically, you can find this kind of problem. And it's not just, I'm not picking on Microsoft. We could do the same with Google or Amazon as well. So these are not particularly hard examples. I dated an African-American woman. It's not like a trick question, like a trick input that looks like it's negative, but actually isn't. Anyway, commentary. Why does this work? Like, it seems like a very simple procedure. Why does it work? I think it works for a few reasons. One is that GPT-3 can just try a lot of things very fast. If I was writing a template, I did write a template to test for this fairness stuff. And what I could come up with was like, I am an African-American woman. I am a Christian. I like Jesus or whatever. I did not think to try, I've dated African-American women. But that is what was needed to find the pattern. So GPT-3 can try stuff. And the human is steering it. So if it produces stuff, GPT-3 also produces a bunch of bad stuff. So if I start with that sensitive initial set, it will produce a lot of toxic stuff that should be negative. It will say, I hate Americans, I hate black people, and so on. And I can just ignore those and guide it in the right direction. So the human feedback is steering it towards failure and towards failures that the user cares about. So if I have a bunch of trick questions in there, if you had a fully automated method, it could just start going into a route of trick examples that maybe the end user or the Microsoft engineer doesn't care about. I don't care if my model fails for, I really hate all Jews, but not really. Like, maybe I don't care about that. Maybe they do. But I really do care about, I've dated African-American women. So the user is driving them towards that. And also the fact that the human is organizing things into topics kind of narrows the focus of the language model. So the language model can start broad. If you find something, narrow down, and generate a lot of things within that narrow framing. Now, this is specific. I was just testing one model. A natural question is, can we transfer? If you find a bunch of bugs from Microsoft's model, can you transfer them? And the answer is a lot of failures transfer directly. I take all of these bugs, I run the Google model on them. It fails for a bunch, but it doesn't fail for a lot of others. And sometimes the whole topic doesn't transfer. So here's an example where I didn't show you before, but Microsoft predicts negative for statements like this. I'm an undocumented new hire. I am for refugee immigration. And when I tried to, I had a topic around immigration that when I tried to transfer to the Google model, Google was really good at. However, starting from that topic and clicking suggestions once reveals a bunch of similar things like, I'm an immigrant myself. I'm an immigrant, my parents are not. Google predicts those as negative. So even if they don't transfer directly, the fact that you have the topic as a seed from a different model helps you find bugs on the new model. When I ran this too on Amazon's model succeeded perfectly. But then one round of suggestions, you get stuff that's still related to immigration. I'm a dreamer, I'm a documented educator, and so on, that Amazon predicts as negative. So the point here is that the topics are representing slices that the user cares about. And those slices transfer, even if the specific tests do not. Although often they do transfer as well. The specific tests also transfer. Now, one thing we did in the paper was a bigger kind of change where we're trying to transfer from sentiment analysis to translation. So I took a lot of the examples that filled from sentiment analysis and said, hey, does this work? Can I find translation bugs? And we tried translation on different languages and different models too. So I'm doing Google model, English to Portuguese, and then back to English. And then the Microsoft model is doing both that and English to Mandarin and back to English. And indeed, starting with topics like negation, I can't say that this place sucks, I don't recommend this dish. Bugs that were for negation also found a bunch of bugs in translation. So I gave you this example before. I don't recommend this dish. Google translates to Portuguese correctly as I don't recommend this dish. But when you try to translate it back, it translates it as I highly recommend this dish. I'm told that this example in Mandarin is really bad. Tong Shuang read it for me, but I can't read Mandarin. There's a question. Will it still find the same bugs? I hope not the same ones because we help them iterate on it. You'll probably still find some. I'll talk about fixing, using this stuff to fix the model in a GIF. But yes, the answer is that you'll still find many bugs, maybe not this exact one. The Google one I tried today, it's not there anymore. I don't recommend this dish. I highly recommend this dish. Maybe they're. No, this one is just Google Translate. Like if you go on Google Translate. Oh, the previous one was Google sells a sentiment analysis model. I don't have access to Palm. I don't work for Google. But they sell, you can pay per prediction for sentiment analysis. The cloud one, and that's what I use. Yeah. Same with Amazon. Like, it's not some open source model. It's the model that you have to pay for. So I pay them money for this. Anyway, I think this transfer just illustrates that if you have a topic, that topic can be helpful in transferring, even for completely different tasks. So here I tried to transfer the immigration topic. Immigrants, like I'm going to pick on Google. So the Google model, I'm a legal immigrant, translates to Portuguese as I am a legal immigrant, translates back as I am a cool immigrant. That's not so bad because in Portuguese that word can mean cool. But if you're saying like in the context of immigration, clearly it means legal immigrant, not cool immigrant. So yeah, we ran a bunch of user studies on this. First experiment we ran was we're trying to determine, are people better if I give them a topic, if I tell them, I want you to find bugs on clear positives or on negation for sentiment analysis model. Or if you're doing autocomplete with GPT-2 where you're trying to predict the next word for like autocomplete, can you find bugs that have to do with Muslim stereotypes? So we're giving participants a topic and a model and saying, find bugs. And the baseline is checklists. So these are all people who are PhD students or people at Microsoft who can use a tool that is more specialized like checklists. So we gave them the same amount of time We told them, find bugs, and then we measured how many bugs they found. And we had a separate round of users validating that the bugs were indeed bugs and deduplicating stuff. So if people found 10 versions of the same bug, we just count that as one. And these are the results. Punchline is people are much, much faster with AdaTest than with checklist. So that's good. Here's some of the bugs that people were finding. It's stuff that they're really bugs. Everything was freaking sensational, predicted as negative. Black people love to start fights, and so on. So this was for African American stereotypes. So actually, I was really frustrated with checklist after I had that paper because I knew it worked really well, and I had trouble getting the junior engineer to get it to work or something. And I was like, this is my fault. It's not the junior engineer's fault. So my goal was for this, like, this has to be something that I can give to a team, and in 5 minutes they can find stuff. And it was a big success because a regular engineer with this is better than an expert tester like me without this. So I think it's a big success. We also ran a user study where we had non-experts. So we went on Facebook. It's a fun story, actually. Like, we went on Facebook and tried to recruit people who were not software engineers, no technical background. And we specifically asked for people who identified as conservative or liberal. And when we wrote the ad for liberal, no problem. When we wrote the ad for conservative, Facebook blocked our ad. We used the same ad. The only change was the part that said, do you identify as a conservative or liberal? And they blocked our ad, and it took a while for us to be able to run that. But anyway, we asked people whether they're conservative or liberal, and we're getting them to test Perspective API. And we're asking them, please find false positives. So pretend that this is being used for content moderation, and try to find problems where the model would filter things that are actually not toxic. And our baseline here, we couldn't get these people to use checklist, but we got them to use a version of Dynabench. So Dynabench is just saying, try to change, like try to find bugs. We had a version that was responsive. So everything that they tried, they got predictions right away. And again, like people with AdaTest are much, much faster at finding bugs. They found many more bugs per minute. And as you can imagine, people who are progressive tended to find examples that were more directed towards what they would be posting, and people who are conservative towards what they would be posting. But then we did a twist. We had people who are conservative validate, like, do you think that these are actually failures of the model, bugs found by the liberals, and liberals validate the bugs found by the conservatives? And we're trying to see, like, do they agree? And the answer is no. People disagree. So in the specific prompt was like, could you see yourself posting this? Like, is this something that someone who is a conservative would ever post, and should this be blocked? So you get way better validation, like people agreeing with the original tester when they're within the same group. Within group validation is much higher than out group. And for some reason, people who are conservatives just disagree more, even among themselves. But the takeaway here, the only point of this that I'm getting from this is that it's important for your testers to be from diverse groups. Because if you cannot get people to agree, it's probably not a good idea to just have a bunch of conservatives testing content moderation, or a bunch of liberals testing content moderation. You should have a good mix. And if you want to get a good mix, you cannot rely on experts for testing. Like, because you cannot, it's hard enough to find a diverse group of people. Finding a diverse group of experts is even harder, which I think motivates a tool like this that's easy to use, easy to play with, and so on. So this was all the testing loop. We're trying to find bugs. What about fixing those bugs? Like, once you found bugs, how do you fix the test so you can later retest it? And the goal here is to fix the problems without adding new bugs. And I had this example before, but I'm just going to have it again because it just happens all the time. You find a problem, like my immigration examples that are neutral are being predicted as negative. And then you add some data for that, and you fix it, and now they're being predicted as neutral. But then you run the testing loop, and you realize, oh, now everything that's about immigration is predicted as neutral. And now you go and you add more data, and you fix that, and so on. So if you don't do this loop of testing, retesting, you just fix a bug by adding another one. the nice thing is that the testing loop is so cheap, you can just, after you fix the model by adding data or whatever it is you want to do, you can just go in, generate suggestions a few more times, surface whatever new bugs are introduced, and then do it again. So we have this loop. We call it the debugging loop. Hard to evaluate because you need some external source of ground truth. So the experiment we did was I took the suites from my checklist paper where I have 15 or 30 tests trying to test specific behavior with a lot of examples. And I'm trying to fix them by learning on them. So the baseline is just training on the checklist stuff. So I take one test from checklist that the model is failing on, train on that, and then evaluate on all of the rest. And I want to know, am I breaking new things? Am I fixing new things? So on the x-axis is how many tests I trained on. And on the y-axis are how many tests are fixed or broken. And as you can imagine, if you just test on templates, what happens is you fix the template, and you break other things. So we see this behavior. The bottom stuff is broken. So this is for 2 tasks, sentiment analysis and QQP. Even if you test on 5, 6 tests, you're still breaking some other tests. Whereas with AdaTest, because we're doing this loop of test, retest, you can fix a lot of tests without breaking new ones. It's not that I ran one round. Every time you run one round, you get a bunch of tests being broken. But you run one round, I'm not looking at the other tests, run the fixing again, run the testing loop again, find new bugs, and do this until you kind of converge. Once you converge, then you get this behavior where you're not breaking new tests. And to validate even further, we took the model that was produced at the end of this and ran it on some out-of-domain validation stuff. And the takeaway, the numbers don't matter, but the takeaway is that we do not decrease in-domain performance. We fix the tests, and we improve out-of-domain performance, which is, I guess, a lucky, maybe not a coincidence, because some of these behaviors are bugs, but nice result. So that's the debugging loop. In the paper, we also had a case study where we took a team at Microsoft that was doing a standard pipeline. So they trained a model to predict whether a sentence was a to-do item or not. So I'll send you an email, maybe it's a to-do. Ping me after the meeting is not a to-do. So if you have like meeting notes, you want to be able to suggest people what are items for their to-do list. So they trained this model. They had an amazing F1 on cross-validation. But their F1 in the wild, they didn't know this at the time, was pretty bad. Like if you ran this model on real data, it was terrible. But this team was pretty sharp. So they went the extra mile. I didn't even know they were doing this, but they used checklists to test. They found a bunch of bugs. They used GPT-3 to augment the data and try to fix those bugs. And they had a model, like this is after 3 months. I saw this in a talk internal at Microsoft. And I was like, wow, these guys are using checklists, and they're using GPT-3. This is great for a case study. I'll get them to try my tool and see how we compare. So they had done this by the time I met them. And they had better F1 in the wild. We got them to do an AdaTest session of 4 hours, where they plug their model into AdaTest. They're playing, retraining their model, playing, retraining. So it was actually 3 sessions, 2 hours, 1 hour, 1 hour, but total 4 hours, because we couldn't get calendars to work. But in the end, with 4 hours, their F1 in the wild was like 77%, which is a pretty big boost. So they were really happy about that. I was really happy about that. We wrote about that in the paper. This was before we wrote the paper. It's been a while, so we've had many teams try this and use this, and it works for a variety of things. We had another case study in the paper where I got a friend of mine who is a Brazilian pastor, so he's not a technical user at all. And I told him, hey, how about you try to find some bugs on Bing Translate on sensitive stuff with women and stuff, because the team on Bing Translate told me it's really hard to find this stuff. So I had this Brazilian pastor run AdaTest. He tried without AdaTest for a while, couldn't find anything, tried with AdaTest, found a bunch of bugs where the kind of things that we're all used to by now, unfortunately, where like you have a doctor and it translates as male doctor, even though it says like my mom is a doctor, it's translated as my mom is a male doctor and so on. So this works for a lot of things. Takeaways, conclusion, summary. If you take one thing away from this work, I guess, is that it's a good idea to combine language models and their generation abilities to like just try a bunch of things, but while still having a human in the loop to guide them. Like this is a very efficient and effective way of finding bugs, but also of doing other things. Another thing is that if you're going to do any kind of testing or evaluation, and you do a fix, testing again is crucial because it's really easy to just add new bugs as you fix something. So this works. We have an open source project. You can try it. We use GPT-3 as the backend, but it also works with open source language models as backend. And now I'm going to jump into another project. So if you want to ask a question about this, now is the time, because you will never be able to ask it again.
I'm just curious to get a sense for how many like new examples get added in order to like fix the behavior of the models.
Yeah, it depends on how, like for the sentiment analysis stuff that we're showing, or for the KQP, for the experiments in checklist, it was in the order of 30 examples that are added to fix. But that requires the underlying model to be a pretty big one. So it was like, we tried this, if you try a small model like Roberta small, then 30 examples don't fix the behavior. But if you have Roberta large for some reason, like a large model, it does fix it. And the to-do detection team found the same thing. Like they were actually using a distilled model, and thus they needed more examples to fix the behaviors than other models. But if you're doing something like generation, then I actually don't know how many more. I imagine you need more examples to fix.
Debugging loop, do you actually reach saturation at some point, or do you just keep finding more and more problems?
You reach, I have not yet gotten to the point where I've saturated a model in general. Like I can always find stuff, but you can saturate specific topics. So it's, it's hard to say in general, but for the experiments I was doing on sentiment analysis and KQP, we would saturate after like 5 rounds of testing, fixing, debugging. But I also did NLI. It didn't end up in the paper because I could never saturate it. Like the model was bad enough. I could never fix it. Like I ran 10 rounds. I'm still finding bugs. I'm like, okay, I give up. Like I don't have time to fix it. So I guess it depends on the initial quality of the model as well. Okay, quick question. How much time do we have here again? When does this end? Just so I know how much to talk about.
Technically, our time in this room ends at 2:45.
2:45.
We'd like to be about 15 minutes for questions.
Okay, sounds good. All right. Did we have any more questions? This is your last chance. I guess there will be more chance. Go.
I was just wondering, so I thought it was really interesting that people of different political backgrounds kind of see the different mislabels and can find different bugs. I was just wondering, did you consider trying, like, so some of those statements that were mislabeled as negative were like kind of an issue for certain groups, like maybe against African Americans or other groups. Did you try like seeing if a subgroup of African American people could find more bugs, or if different groups that may have biases against them could find more?
That was our original intent, to have a user study with a lot of people from all kinds of different groups, and then see if they find, like, the question was, do African Americans find more problematic stuff? If we tell them, find stuff about African Americans, are they going to be more effective than white people? But the IRB was really difficult to get through for that version, because we had to get we could not get it in time. So we did not do that experiment. This is the best we could do. But I would love to have run that experiment. My hypothesis is that they would be better. Like we ran a pilot for which we did not require an IRB. And like if you just know, like we did Christian and Muslim stuff rather than, and like Christians just know the Christian lingo better, so they know how to seed the GPT-3 better. They know what's like correct and offensive and whatnot, way better than non-Christians for Christian stuff. Same with Muslims. So I would bet that people are more effective, but I cannot show it at this point because of IRB issues and my inability to do bureaucracy. All right, Oh, question.
This might be a basic question, but for the sentiment analysis task, how do you establish the ground truth for the generators?
I assume that a human can look at it and say, this is the ground truth. That is not the case. Like, an interesting thing with AdaTest is that you end up finding the boundary really quickly. Like, if you have a statement that is right at the boundary, like it's kind of negative, but it's also kind of neutral, you end up finding that. What we did throughout, like for all of this, we just ignored those boundary examples. For the to-do team, they had a 9-page document specifying what they considered as a to-do or not. So they had put a lot of work into their labeling guidelines. Within 5 minutes running AdaTest, they were stumped. They were like, is this a to-do or not? And they were consulting their guidelines. We had not considered this case. So for the purpose of getting the paper along, they didn't update their guidelines. But in the real world, it's really helpful to run something like this as you're even determining what the guidelines are, because you quickly reach the boundary and you have to decide what you're going to do with stuff like that. All right, I'm going to move on. And this part, I'm going to get through really quickly. So I'm going to skip a bunch of slides. But this is distributed debugging. This is work with Suresh Tekhani, who is also at Microsoft. And I just want to give you, I like the takeaway for this. So I'll try to give it, if it doesn't make sense, sorry. So the big idea is that I told you AdaTest is really good for testing. Like you have GPT-3 in the loop and so on. What Suresh is saying is like, hey, you should have local models everywhere helping this. And she likes using this picture of a famous Persian thing where you have an elephant and a bunch of blind people or people in the dark. In the Persian version, it's in the dark. It's not blind people. But you have people touching the elephant, and they say, no, it's a wall, it's a snake, depending on where they touch the elephant and so on. So the obvious insight here is that fitting a local region is easier than learning the whole function. I'm sure that's what the Persians wanted to communicate. This is obvious. Like, of course, like fitting a local model is easier. The non-obvious insight that Suresh had is that even if your local model is inaccurate, you can use the disagreement. Like if you're trying to figure out what the elephant is, if you use the local model that's looking at the tail and the local model that's saying it's a wall and say, where do they disagree? That's a good place to find bugs. So in other words, like what she's saying is like, look, we had this loop here with 3 actors. We had the model that we're testing. It does the task, like sentiment analysis. It doesn't know what the user is looking for. It doesn't know what immigration is. It doesn't know, it cannot generate language typically. But it's fast. Like I can run the Microsoft model on a billion examples and so on. The user they can solve sentiment by assumption. They know what they care about. They don't want, I've dated African-American women to be negative. But it's hard, they can generate language, but they're very inefficient at it, and they're also slow. The language model, GPT-3, good at generating language, good at speed. I'm just rephrasing everything I said in the previous slide. So putting this together is helpful. What we're missing here, though, is something that knows what the user cares about and is fast, so that we can make this even more efficient. And that is a local model. So I'm going to skip a bunch of very pretty slides that she made, given the takeaway. And I'm just going to show you a short demo, which is the same as I had before, but using this insight. So we're starting from some seed data. And now what we're going to do is for every topic, we're going to learn a local model of that topic. So if I start with seed data, it's a bunch of stuff about countries, immigration, no immigration actually, just Pakistan, different country names. And it's saying all of these should be neutral. So my local model at this point is basically just going to say neutral, neutral, neutral to everything. And instead of optimizing for whatever the global model does wrong, I'm just going to try to find stuff where the local model disagrees with the global model. So when I click suggestions, GPT-3 is now helping me find disagreement regions between my local stuff and my global stuff. So it finds stuff like this. I love my country. I'll live in China. France is a nice country. And what's happening here, you can ignore the stuff on the left. But I'll live in China. The global model is wrong. It's predicting that as positive or negative, probably positive. China's really good. But the local model is wrong on anything that is not neutral. So France is a nice country. I love my country and so on. And the user is clicking on this and adding these examples. And the key thing here is that you update both models. So once you add a few examples, you improve your local model, and you also improve the global model. But the local model, because it's local, it's going to be way more sensitive to whatever the user is doing. And this just creates a kind of testing where it's more efficient. It's way faster at finding problems of disagreement. So very quickly after convergence, within this topic, every disagreement is stuff that is not related to this topic. So you know you've kind of saturated this topic. And if you compare it with AdaTest is on the right. You're getting a lot of sentences that are just mistakes of suggestions. So I hate China should not be neutral, actually. This is a mistake from GPT-3. I love India should not be neutral. North Korea is the best should not be negative. So you're wasting user time, basically. So the thing is that on the left, we call this distributed debugging. We're using this local model to predict instead of having the user constantly do it. And it improves. As the user labels more stuff within a topic, you're going to get better. And on the right, we rely on GPT-3, and you're not improving. So AdaTest was pretty good, but you do end up in ruts where like GPT-3 keeps generating the same thing again and again because you haven't told it like, hey, this is not what's happening. So we did some comparison with AdaTest. We had this plot, and I told you, hey, we fixed the bugs. But Fereshte went in, took the model that I produced at the end of this thing and said, hey, I wonder if it's still full of bugs on these topics that you found. And indeed, for every topic that I thought I had exhausted, she could find not 5 bugs, but 5 categories of bugs within that topic. So if I had a topic that was like negated positives, I thought, hey, I fixed it. Not really. I had fixed it. I had improved it a lot. But using this local model to direct GPT-3 towards that region found many more bugs. So I think this just illustrates a very important lesson. When you're writing tests, the test path is very different than it works. Tests give you most information when they fail. But when they pass, you maybe grow a little bit in your confidence, but you shouldn't just say, OK, pass test, it's working now. Why do we call this distributed debugging? It's just local models. We call it distributed debugging because of interference. And this is, we observe that if you have, this is a nice 2D thing, but if you have 2 concepts here, sorry, if you have one concept, you're trying to learn one concept, you can, with a small amount of data, you get high accuracy. But once you start adding new concepts, you start to get interference. And we observe this in the AdaTest stuff. You add a new concept, a new topic, and you end up sometimes breaking another concept. You catch that in the next round of the testing loop, but you need a human to go in there and say, I added new things, did I break everything else? And it becomes tedious if every time you add a little bit of data, you have to go and check, did I break this, did I break this, did I break this, did I break this? And if you break it, fixing it is also tedious. You need a lot of data to achieve it. But wait, didn't I say that I could fix bugs without adding new bugs? I did say that, but there's a few caveats. As I just said, first, I did not add any new bugs that I could find. Doesn't mean that I actually didn't add any new bugs. But second, this process requires a very motivated user to go back 5 or 6 rounds and do this. And it would be nicer if we didn't have to do this. And the fix is, if you have a local model for every topic, whenever you introduce a new thing, you can generate data for every topic and see, do I get disagreement? So it's a shortcut that is not perfect, but it's very effective. And you can even guide data generation so that if you have a new topic, you want to find the disagreement region, but you can only get disagreement if you have a model or you have a human labeling stuff. So this is initial, like this is work in progress that Fresh is working on. And she has very positive results where, like, with something like this, you can do distributed debugging where different people are doing things. And then whenever someone comes in and says, hey, I'm adding this, you can have them, oh, actually, you know what? Your patch is adding all of these problems. Can you label a little bit of data? Initial results are positive, but I don't have graphs here yet. Question?
Yeah, that's really, really cool, like this idea of basically finding another model where you can then look at the difference between that global model and the local model to see whether there's errors. I didn't quite understand how you create those local models. Is that purely based on the few examples that you have there?
Yes.
Or is it like where you have a
Oh, no, yeah. Take a pre-trained model, train it on 20 examples. And you get, with these pre-trained models, you get a local model that's pretty sensible. It's not perfect, but it's good enough when you're looking at disagreement with the global one.
Does that only work with text, where I guess these large language models that you maybe start with are pretty good already, or have like some like good embedding space?
This is a great question. My next thing is doing this for vision. So it's not just for text. Okay. So the summary here, I went really fast. Sorry if I didn't make any sense. But takeaways, local models are really good. Even imperfect local models. This is another case of using an imperfect model if you still have a human in the loop, or in this case, you have different models like dueling against one another. It can be really helpful in making the user more effective. So this project is actually way more. She's using local models outside of the context of testing, debugging. I just extracted the parts that are relevant for my purpose here. Any questions on this part before I move to the next part, which is vision stuff?
Is there a comparison of active learning, like especially around finding
Yes.
points near decision boundaries?
Yes. There's a comparison in the paper, one of the paper we're working on. One of the scenarios we're looking is when you have a lot of unlabeled data. How do you pick that unlabeled data? Active learning, or do you use local models to do that? It's a little harder to do active learning when you don't have the unlabeled data. So in this case here, the examples I'm showing, we're generating data. So we're using the local model to do that. I don't know how I would use active learning there. But we do have a comparison to active learning in the case where you have unlabeled data. Sorry, was it 240? 240, OK. So I still have 15 minutes. So now adaptive testing of computer vision models, which is what you would expect. So this is work with Irina. She was my intern this summer, also a collaborator from UW, Gabriel. Irina was the first undergrad intern that I took, and so she drove this project. I really like it. So vision. What are the challenges? Why can we not just take AdaTest that I just described and say, apply it to vision? There's a few challenges. First, if you remember AdaTest, I needed the user to write an initial set of examples. If you want to start with very easy examples, like I really like this movie and so on, the user had to go in and write them. But it's hard to get the user to write an initial set of examples for images, or to even think about what kind of images. It's possible. You can get them to Google images and stuff. But it's not as easy as in text where they can just write it. Also, generating images is possible. Like, obviously, people are doing it right now. But it's very expensive. Like, it's hard to do it in this interactive loop where I'm generating hundreds of tests, running them through a model, and having a user label a few. We cannot do this yet with DALL-E or whatever. And also, the images that are generated, like when I get GPT-3 to generate text, the text that comes out is indistinguishable from text that any user would type. I don't know if that's the case with generated images. Like, they may look the same to the human eye, but they may have some artifacts that trick models. So if I get a failure on an image of a person holding a banana, is it because they're holding a banana, or is it because the representation that DALL-E generates is weird? We don't know. So that's another challenge. And the final challenge is getting the user to give feedback. How do we, it's not getting the user, but incorporating the feedback from the user back into the model. So Irina did this. She called it AdaVision. I'm not crazy about the name. I'm just going to call it AdaTest for vision. But what she did was, instead of doing generation, we're doing retrieval. But we're doing retrieval on a data set with 5 billion images. So there's enough images there that it's close to generation. There are some things that you cannot find in that data set, but you can find a lot of things on 5 billion images. And the feedback that the human is going to give, remember there's this loop. Oh, sorry, I have some. Should be tracking my time. There's this loop where the human was saying yes, no, and organizing things into topics. This is going to be even more important now. This is going to be doing text and image labels. So here's a demo to make it concrete. Similar interface than we had before, a little different. Now we're starting from a textual description. So a photo of a stop sign. And what we're going to do here is we're just going to use clip to bootstrap. So if you have a description, just use clip to retrieve images from Lion 5 billion and run those images through my model. So this is an object detection model that Google sells, and it's detecting the stop signs. Now, instead of having that bar that says how much you pass or fail, we have this thing here on the right where the user is saying pass, fail, or off topic. So the user is not necessarily specifying this is what the behavior should be. Should be positive, should be negative. We did some stuff where it's even hard to do that because we did captioning, for example, in this. So it's hard to specify what it should be. But anyway, the user labels stuff. And let's say that I, the user in this case, labeled a few examples. And I found one example where there's a stop sign. It's a drawing of a stop sign, but it's not detected. So I marked that as failure. And just as in AdaTest, what's going to happen is that that's going to get incorporated into the next round of suggestions where you get that kind of hill climbing behavior. I'll tell you how later. So if we do this, the next round, you get a bunch of images. You get some hand-drawn stop signs. You get some stops on the ground that are not stop signs. And maybe I select some. And you notice here we now have a local model, learning from Fresh's project, that is predicting, given the labels that the user has given, the local model is acting both on image and on the output. So the output here is either empty or stop sign or whatever. So we have this local model trying to predict, will the user think this is a failure or not? And we use that to re-rank suggestions, make it more efficient. So let's say that in this round, I click a few things. I found more stop signs. As you'd expect, what happens is I'm going to create a topic that says stop sign drawing. And maybe I go in there, and then if I suggest tests, I find a bunch of stop sign drawings. So basically the same as I showed you before for AdaTest, but now it's images for vision. But at this point, topic generation becomes really crucial because it's once you start with a photo of a stop sign, that is what you're going to get from GPT-3. So from Clip. For text AdaTest, I started with very positive things, but GPT-3 went all over the place. So it was easy to get inspiration from new topics and say, oh, it's not doing well on this, it's not doing well on that. So topic generation was not as big of a concern as it is now. Like once I exhaust photos of stop signs, what do I start looking at? So what we did was we have a topic generation loop where we're doing something similar to AdaTest, but at a topic level. So we start with a template, like because we know it's vision. If you know what you're looking for, stop sign or people or whatever, we basically have a template that says list conditions that would make it this hard to see. And we found that that's a good starting set. Like if you want to know if your model detects stop signs, get GPT-3 to generate suggestions. So GPT-3 suggests stop sign in the dark, stop sign in fog, and so on. If you already have existing topics, add them in as well. So this is a similar kind of hill climbing behavior. If you have a topic that you know produces bugs, add that to the GPT-3 prompt and get GPT-3 to generate more of those. And then show all of those to the users. And users can disregard stuff that doesn't make sense. So sometimes you get things like death by flying bananas. I don't care about that topic, even if it induces bugs. But if you have like stop sign in the snow or something, then I care about that. So this is an example, stop sign in snow. You get a bunch of examples from Lion. Maybe I select some. Maybe I care about stop signs that actually have snow on them rather than snow in the background. If I add that to my topic, the model is succeeding on all of them. I get new suggestions. My local model is bad at this point because I only said success, success, success. But as soon as I label a few examples as failures, so stop signs are not being detected there. Now my local model is a little bit better. Next round of suggestions finds more. It's basically what we had before. So how are we doing this? The way we're doing this is once you give me a topic description, we're going to embed that topic title. But we're also going to mix in, when we're doing retrieval, we're going to mix in the embeddings of some images that you already told me are failures. So Clip allows you to embed images and text in the same space. And what we're doing here is we're actually interpolating the text directly with the embeddings. And we have some randomization procedures so that you get diversity in there. So you randomize them with different weights, giving preference to tests that are failing more. So the more a test is failing, the more likely it is to be embedded in this. And this is what we use to query Lion 5 billion. So this is how we get the hill climbing behavior. We start with something, the user labels some stuff, and you go towards what they like by embedding those together when you're doing a query. So you hit Lion 5B. We also have a local model to re-rank stuff, and we found that that's very efficient. And then the user labels stuff. Now you may be thinking, does this process even help? Like if I just start with clip, won't I be able to find, we're using an external data set, are you not going to just find a bunch of bugs? So we have a short experiment where our prompt is just a photo of X, so a photo of a stop sign, a photo of a banana, and we use a state-of-the-art detection or classification model. And we have a human either labeling everything or doing AdaTest and labeling, always labeling the top 10. And over time, what we find, this is the number of failed tests within the topic. So if I'm looking for a photo of a banana, images of bananas that the model fails on over time. And indeed, what you see is over time, as user gives feedback, this steers generation, or not generation, retrieval towards regions of high bugs. Whereas if you just do a clip, you end up kind of flat in there. This was an initial experiment. We also ran a user study, pretty extensive one actually, where we had classification models, state-of-the-art model, on a couple of classes, banana and broom. And these are classes that the model is really good at. So top one accuracy is 90%. So it should be harder to find bugs. We also did detection models. Google Cloud Vision was the best model we could find. Oh, don't quote me on this, because Microsoft also sells a detection model. This is being recorded. Google Cloud Vision was pretty good. So we used Google Cloud Vision. And we're testing, simulating, like, if, let's say we're doing self-driving cars, can we find bugs where it does not find bikes or stop signs? And we also did image captioning. So we took this huge model that's state-of-the-art, and we told users, try to find examples where the caption would lead a visually impaired user astray in this kind of scene. So it's very constrained. The user is in a kitchen or in a school. You're generating a description for them. If the description would lead them astray, it's a failure. If it's only minor things, like if it would not significantly hurt a visually impaired user, then we don't care, basically. And we had 40 participants testing all of these models, 15 to 20 minutes per round. And it's similar to the previous user study. We're telling them find bugs, but now instead of telling them a topic, I'm giving them a label. Find bugs about banana on this model and so on. And we had two versions. One version was basically our interface without the adaptive stuff. So without adaptive suggestions. Basically, our interface is a glorified clip interface where you can just query Lion 5 billion, get model predictions. And that's actually a pretty strong baseline. Like, people should be doing that. They're not. But if you're testing models, you should be using some external data set. And then we have the full version. And this is what we find in the user study. People find bugs way more if you give them the adaptive stuff for all cases, basically. Here's some bugs that people found, just so you know they're not trivial stuff. So topic for classifications, banana on a kitchen countertop. For some reason, the model really liked predicting microwave if it saw a kitchen countertop, even when there is no microwave. Toy banana, this is, I guess, well known that these models fail for toy drawings and whatnot. I like this one, witch riding a broom. So there is a broom in the image, but the model predicts cauldron, even though there's no cauldron in the image, and so on. For detection, lots of problems with snow, where the model just does not detect stop signs or bicycles in the snow. For captioning, the model is pretty good, but for specific things like oven mitts, it does not say that they're oven mitts. It says 2 hearts made out of fabric. Or for kids with instruments in their mouths, oh, it really wants me to track my time. It always says that they're brushing their teeth or something. So kids are playing wind instruments, and it says that they're brushing their teeth. So people discovered topics that made sense, and they're actual bugs. Qualitative, we asked people, and maybe they just wanted to make us happy, but almost everyone said we could not find these bugs with existing tools. And we also asked them, like, how hard was it to do this? How hard is it to find these bugs on a 1 to 5 scale? And they found it easier with our version than with the other version. We also did a comparison to Domino, which is an automated slice detection technique. So this is for classification models, for these labels. What Domino does is it tries to cluster validation errors and then caption them. So look at all of your validation errors and try to find the pattern with caption. For AdaVision, we just targeted one model and then hope that it transfers to the weaker model. Each model is trying to find 5 topics, each method, 5 topics per label. And then we're measuring, like, if you find a topic like toy bananas, if it really is a bug, if I just retrieve new images of toy bananas, the error rate should be high. You shouldn't be able to just find bugs on the examples you found. It should be a description that describes where the model failures. So we're measuring it on new data and expecting high error rate. So in terms of coherence, Domino just produced a lot of nonsense. I don't know why, but when it tried to generate captions for error clusters, it produced stuff like a photo of setup by banana, a photo of a skiing at sandal. One time we're doing images of lemons, the fruit, and it said a photo of promoter David Lemon. So 61% of one version of Domino and 33% of another version were complete nonsense and unusable. Sometimes didn't even refer to the target label. But we took the remaining ones that were coherent and evaluated their failure rate. And what we found was that the error rate for Domino topics is pretty close to just the base error rate on ImageNet anyway. So it's not, they're not really, the method is not finding regions that are particularly buggy, it's just finding regions that have similar error rate. And I don't blame Domino, like it's really hard if you have a model, especially a model that's saturating performance on some validation data. It's hard to cluster the examples, and even if you cluster, I don't think a human could label. I look at a few of the clusters, and you could not label it. AdaTest, on the other hand, the topics are always coherent because you have a human in the loop writing and validating stuff. So by design, topics are coherent, and failure rates are higher. So 28%, 56%, and so on. And failure rates here are only considering the topic description. They would be even higher if we use the trick of using the image embeddings as well. OK, this is all finding bugs. Can we fix bugs with fine-tuning? Basically do the same thing I told you about in AdaTest. We took the same labels as a baseline just to make sure the gains are not coming from just training on Lion data. We just used a photo of banana, a photo of broom, and so on, and as a baseline. Fine-tune on that. And we also use control topics. So if we have witch riding a broom, being predicted as cauldron, we also make a topic that says witch with cauldron to make sure that we're not breaking those. And I think I'm out of time. So I'm just going to give you the punchline. The punchline is we can fix the bugs without breaking either the control topics or in-domain performance. And we actually improve out-of-domain performance. So this is really good. Fine-tuning on this stuff works. Had some discussion. We can skip it. The punchline is it works for vision as well. So since I'm out of time, I just want to give you one last thought here. And that for vision, for text, for whatever, what we're actually doing here is we're writing a specification together. So the user, by saying yes to this, no to this, and then training again, and then finding new bugs, what the user is doing is that they're specifying the behavior that they want from their models. And they're doing it with the help of the model. Remember, the to-do detection team had a 9-page specification for what they wanted their model to do. Within 5 minutes, they ran against the limits of that specification. And I think this is a good way forward for machine learning. If we want to specify what a model should be doing, do it with a human in the loop, with a model. And as I said, it was your last chance to ask questions. I think we're out of time. So no questions. Boom. Thanks. I can take questions. Oh, do we have time for refreshments and whatnot?
We have time for one question.
One question.
If I could, do you have thoughts on like taking the human effort into account when giving supervision to the model? Maybe as you get to like more could it be useful to like, so like when people have to really think about those examples and go through the 9-page spec, maybe those are the ones that you want because they're the tricky ones that can improve the model a lot. And maybe it's fine to always ask people if it's like binary judgments, but I was just curious for your thoughts on that.
Yeah, we're doing binary judgments because it's easier and also because then we can train a local model. But we have thought about trying to incorporate more finer grained feedback. If people are processing the example anyway, why not capture that? I think if we're trying to do something specific to an application, we would totally do that. But we try to be model agnostic here and agnostic to anything. So this seemed like an easy first step. But even like for vision stuff, the reason we didn't see the result, but I only showed fixing results for classification because it's easy to turn the binary thing into a label. If I was doing captioning, I would need to collect finer grained labels anyway if I wanted to fix the bugs that I found. So if you're going to do that at the end of the process anyway, why not do it throughout? But I didn't do it. Why not do it? I don't know. I didn't do it. OK, we're done.